All right, in this video, we're going to be connecting position, velocity, and acceleration. So kind of something we've already done before, but now we're going to tie these ideas together with integration. So hopefully you recall some of the stuff we did back with particle motion in Unit 4, but that's before we knew integration. And now that we know integration, we can add some more stuff to this idea. So in our study, we got to remember that particle motion, it's given along a horizontal line or a vertical line. If s of t, sometimes that's x of t, that's our position, then the derivative would be the velocity, and the derivative of the velocity would give us the acceleration. So that should be something you already know. So in class, I'm going to do a demonstration of this, and I'm going to put different numbers on the number line on the board. But what I want you to try to think of, or trying to visualize this, is your teacher moves along a straight line in front of the classroom according to these values. So at when time is 0, the first time, we're at position 2. So here's our number line. We start at 2. All right, and then after 1 second, now the position is at -2. So it started at 2, walked to left, now it's at -2, and then at the next second, it's at time 0. So it starts at 2, then goes to -2, then goes to 0. So far I've traveled, looks like 4, 5, 6 units, correct? And then after the next time, the next second, I'd be at position 3. And then walk a long ways. Now I'm at position 18. So it says, how far was your teacher's ending position from his starting position? So what is the difference between I started at 2, and I ended at 18? So that change would be 16. And then what's the total distance your teacher traveled from 0 to 4? Well, it started at 2, went left to -2, so that's 4 units, plus, I would say another 2 plus another 18. So if I added all that together, we get 24. So that's the total distance traveled. So the first idea is displacement. How far is it from the initial position? That's displacement. Total distance traveled is something else. If I add up all the distance traveled. Okay, that's going to come up here in a little while. Okay, this next one you have a calculator. I'm not going to switch back and forth to a calculator because when I do that, it messes up the recording. So I'm just going to mention a lot of stuff what I'm doing in the calculator, but this is going to be better if we do it in person. So a particle moves along a horizontal line. The velocity is given by this function, which is a disaster. It's a lot going on there, but it's calculator active, so keep that in mind. The position, we're going to call that s of t, and it's known that the initial position is -3. S of 0 equals -3. Okay, find all the values of t on the interval 4 to 7 for which the speed of the particle is 5. So there's a couple things we got to know, right? I have to remember, and this is on your memory sheet, that speed is the absolute value of velocity. So I'm trying to find where is the speed, where is v of t, in absolute value, equal to 5. So what I'm going to do in my calculator, I'm going to open up the y equals, and for y1, I'm going to type in the absolute value, which I press math, I go over to numbers, I think it is, and I press enter, and I do absolute value, and I'm going to type in, instead of t's, I put in x's, but I'm typing that v of x. Plus 2x sine. Make sure you're in radian mode. X squared over 12. That's all in absolute value. And then for y2, I'm just going to type in 5. And then I'm going to find where those intersect. To find out where they intersect, let me look at the calculator. I press second, trace, and then intersect. and I'm going to find that they intersect at 3 spots. One of the intersection points is at t equals 3.651, but I don't want to include that because it's not within our range. So the two answers are going to be t equals 5.621 and t equals 6.520, and those are seconds. All right, so that's done in the calculator. Okay, next one, write an expression involving an integral that gives the position s of t, and then use that expression to find the position of the particle at time t equals 3. All right, so this is your fundamental theorem of calculus. And we have to recognize and kind of be on the lookout, if I'm given a derivative or given a function, and I'm given an actual antiderivative value, that should to be telling you that is going to be the fundamental theorem of calculus. So I know the integral of v of t dt, if I'm given when x is 0 or t is 0, I want to find when t is 3, I'm going to use those for my limits of integration. So 0 to 3, that'll be equal to s of 3 minus s of 0, because the fundamental theorem of calculus tells me, since s is the antiderivative of v, there's my expression, there's my equation actually. So write an expression involving an integral that gives you s of t. I guess we didn't quite do that, did we? I guess really we should say this is the integral from 0 to x. I should say t. I'm going to say t, just because it says this in t in a second. You'll see why. And I'm going to say this is v of x, just a dummy variable, dx, is equal to s of t minus s of 0. So s of t would be equal to the integral from 0 to t v of x dx plus s of 0. And that would be an expression that I could use to solve for any value of t, because that's what it's saying here. And then to actually find that for 3, this is what we did over here. So I would say the integral from 0 to 3 vt dt plus s of 0 is equal to s of 3, the position. And I would plug this part into my calculator, and I would get just some number, and then I would subtract 3, and that would give me s of 3 is equal to, I did this in my calculator earlier, negative 6.263, and this is a position. Do we know any units about position? Not really, so I'm not going to write it down. All right, but there is our answer. All right, part C, find all the times in the interval at which the particle changes direction. Okay, so I know the particle's moving to the right if the derivative is positive. If the velocity is positive. It's moving to the left if the velocity is negative. So for it to change directions, v of t needs to change signs. So what I'm going to do is I'm going to go to y equals, I already should have it in there, y1 is equal to this, actually just this part over here, but instead of t's I put x's, and what I'm going to do is find all the x values where it actually crosses over the x-axis, not just touches it, but actually goes from negative to positive or positive to negative. And I did this before, this is going to be better in person, but I would say the particle changes sign or changes directions at t equals 2.341 and t equals 6.127 seconds because v of t changes signs. That's your explanation. That's your justification. So justify your answer. Justification is we know v of t changes signs there. All right, last one on this question. Is the speed of the particle increasing or decreasing at time t equals 7? Give a reason. The following table is fairly complete in describing expressions. Oh, that's supposed to be with the next page, I think. The following tables. Oh, okay, yeah, that's something else. All right, so let's see. the speed, the first thing I thought was v absolute value of t. And then I'm like, okay, where is that positive or negative? This is just what I thought, honestly. And I would think if it was increasing means the derivative is positive, decreasing derivative is negative. But then I remember if it's wanting to know if it's speeding up or slowing down, I need to look at the velocity and I need to look at acceleration. If they have the same sign, it's speeding up. If they have opposite signs, it's slowing down. So in my calculator, I just type in v of 7, just this, or I could look at my table, because I've already had that in for y1, and I know that the velocity is negative 10.2, 12 units per second. And then the acceleration is equal to the derivative of t. So I'd go back to the home screen, I'd press math, I think number 8 to get to the derivative, and then I would plug this function in, and then evaluate that at 7, and let me write this better. That's going to be equal to negative 10.561. So I would say the particle I don't like this all of a sudden. The particle's speed is increasing. So the particle is speeding up at t equals 7 because v of 7 and a of 7 have the same sign. All right, so the next part in the notes is this big table of what all to look for. And it's got like acceleration of a particle at time t equals, and then in how you would write it, acceleration equals the derivative of velocity equals the second derivative of position, the total distance traveled. It's got all the stuff we've done so far. This would be a good thing to come back and look at, just to refer back to. The stuff on the right-hand side, the right column, that would be like your justification or your explanation to prove the questions on the left. And again, that's something we talk about in person. All right, let's do this next question. I'll probably make this 2 videos just so it doesn't stop recording, but we'll do this one now. Okay, the Space Shot is an amusement park ride that gently raises riders up a tower, then rapidly bounces them up and down using compressed air. That sounds awful. The velocity of the Space Shot for time t equals between 0 and 14, including 0 and 14, is modeled by that piecewise linear function. So they're all just straight lines. T is measured in seconds, v is measured in feet per second. Okay. At what times in the interval, not including 0 and 14, does the Space Shot change directions? Give a reason. Okay, this is a video, so you can always pause this, try it on your own, and come back and see if you got it right. But this is what we just talked about, right? When does it change directions? Okay, it changes direction when velocity changes signs. So this one's easier to see since we don't have our calculator. So at 6, at 8, and at 10. So the Space Shot changes directions at t equals 6, t equals 8, and t equals 10. And the reason is because v of t changes signs. You could say something about it crosses over the x-axis. I mean, that's fine. If you say v of t changes signs, you understand the calculus. Period. That was done. At what times in the interval, including 0 and 14 now, is the Space Shot the highest? And how high is the ride at that time? Okay, so if it says the highest or the lowest, that is an absolute maximum or an absolute minimum question, which tells you this is a candidate test kind of question. And I realize I didn't give you enough room to write this down. So I'm wondering if we could kind of go back and forth to this page to write it out. All right, so let's see, and we're gonna try this. At what times is the space shot at its highest? All right, so my candidates need to be, I'll say X, and then I'm gonna say X of T. So I guess, I'm sorry, I should call this T. And then X of T. If X is the position given the velocity. So I know it could reach its highest point either at either endpoints or at all the critical values. And the critical values would happen where X prime of T is equal to 0, and X prime of T is V of T, right? So I need to look, where is the velocity equal to 0? Well, at 6, 8, 10, and then also at the endpoints, which happens to be where it's 0 again. So my candidates are going to be 0, 6, 8, 10, and 14. Okay, the thing that I wish they would have been a little more clear is I want to know for a fact that at time t equals 0, the position is 0. I think it can be assumed because like you have to get on the ride, but does that mean the ride is perfectly flat on the ground or is it a little bit above the ground? We're going to assume that X of 0, the position is going to be 0, and we're just going to say it could be really close to 0, even though technically I don't think it could be at the ground. It could be a little bit above the ground, but we're not dealing with that too bad. All right, so I'm also going to just say that. All right, so this is an instance where I have an actual number on the antiderivative and a graph of its derivative. So this is the v function, right? V of t. So what I could say is that in general, the integral from 0 to t of v of t, or we could call this v of x dx, is equal to x of t minus x of 0. So we will find this part, this is the part we had to come up with, that's going to be the area under the curve for different t values, and we know x of 0 is 0. So if I want to find when t is 0, I'll plug in 0, v of x, we could call that v of t now that we plugged in different t values. The reason these just don't match because they can't match, that'd be like a different variable technically, but it's still fine. That would equal x of t. All right, so that's just 0. On the ground at 0. All right, so let's plug in 6. The integral from 0 to 6 of v of x, dx is equal to x of 6. Okay, so I go back up here. From 0 to 6, what is the area bounded by the curve? What is that area? Now notice the height is 20. So that area, oh man, I lost my green color. Okay, 1/2 base times height, that's a triangle, or do I have 2 of those? That's 20 plus 20, so 40, 60, 80, 100. I got 100. So after 6 seconds, because the velocity, it looks like it was increasing, then it was a steady 20, then it starts to slow down, and at 6, it's at 100 feet above the ground. To find the integral from 0 to 8 of v of x dx, that's going to equal x of 8. So the position when x is 8. So I would take what I had, which was 100, and I would subtract, because now it's going down, 1/2 base times height, that would be subtracting 60. So that's 100 minus 60, so at 40. Because if the space shot was going down, it was going down faster, then it started to slow down, it's still going down, and then at 8, it's changing direction again, so it's going to start moving up. Wait, did I say 6? I meant whatever I said. And then at 10, so integral from 0 to 10, v of x dx is going to equal whatever x of 10 is. So I go back to my graph. That was 100 minus 60. That's going to be plus 40. So that was going to be 80 total. Area under the curve is 100, then minus 60, then plus 40, so 80. And then at 14, time t equals 14, oh, it was going down, so that's going to be subtracting some values. 1, 2, 3, 4. So 4, half of that 2 times 40, subtract 80. So subtract 80 from the one before it, and we get back to 0. So it's back on the ground. So the ride lasted 14 seconds. All right, so the question was, at what times is the space shot at its highest? So at t equals 6, the space shot reaches its highest point of 100 feet. And there we go. We answered the question. How high was the height of the ride? 100 feet. Okay, we got it. All right. Part C, find the total distance of the space shot traveling during the time. So the total distance. This goes back to the demonstration in the beginning when I'm walking around. So if I'm looking for the displacement is the integral of just the velocity from time A to B. The total distance, I take into account how much is traveled total, right? So the distance is going up and the distance is going down. So the total distance, you got to know this, from 0 to 14 would be the absolute value of the velocity. And what's kind of nice is we have all that added up, right? I'm just going to basically make all those positive. So instead of subtracting those numbers, I'm going to add them. So from here to here, it traveled up 100. Then it traveled down 60, but this time I'm adding it. Then it went up, and how much did it go up? 40? So I'm just plus 40. Then it went down 80, but I'm adding the distance, going to take the absolute value. So that total distance would be 280 feet. The displacement is 0, right? It ended up where it started. But the total distance to travel, because it's going up, it's going down, it's going up, it's going down, 280 feet. Okay, write an expression for the ride's acceleration, velocity, and distance from the ground that are valid only for 10 to 12. And this is a very tricky question to me. All right, if I'm looking at that, the acceleration is where I'm going to start. Acceleration there. Acceleration is the derivative of velocity, and the derivative is the slope of the tangent line. So what's the slope there? It goes down 40 over 2. So negative 20, it just says an equation, so no units, so that's fine. It's just negative 20. Constant acceleration, right? It doesn't matter what the time is in between this region. It's on just a straight line. All right. The velocity is the integral of that. So what's the velocity? What's the equation of the line there, right? So I could do it two ways. I could find the equation of the line there, which would be the slope is negative 20, x minus x1 plus y1, which gives me, okay, I'm gonna use the point, I could use several points. Use the point 10, 0. I could use the point 11, negative 20, or I could use the point 12, negative 40. Now, no matter what, I get the same answer. It'd be negative 20, x minus 10 plus 0. Distribute the negative 20, and we get negative 20x plus 200. Oh, didn't fit. Negative 20x plus 200. So velocity is negative 20x plus 200. And I'll show you that we get the same thing other ways. Negative 20x plus 200. If I said negative 20x minus 11 minus 20, distribute that, negative 20x, 20 times 11, that's embarrassing. I kind of, okay, 22 times 11 is 22, tack on a 0, but add it. Then minus 20, I get the same thing. Because 220 minus 20, still 220. Okay, the other thing we could have done is find the antiderivative of this and use a point that we know, which is the same thing. The antiderivative would be negative 20x plus c. Well, I know the x number is 20, or is 10. And then plus c gives me velocity 0, so c is 200. So c is 200. Several ways to do the same thing. However you see it, hopefully you see it one of these ways. Okay, the x of t. Okay, this is the super tricky one that I'm not looking forward to trying to explain. Well, we're going to try it. All right, x of t. We're going to use a similar idea of this right here, right? If I integrate the velocity from some point to any value of t, that would be an equation, fundamental theorem of calculus. So on this one, x of t, for this so anything between 10 and 12, I'm going to use 10 as my lower limit. So I'm going to say the integral from 10 to t of x of x, or we should say s of x because it says s. S of x dx, and it's just x because it's a dummy variable, can't be t, is equal to, no. Oh gosh, I said it wrong. This is not s, this is v, right? We have the graph of v, so I can find the area under the curve, would be equal to the antiderivative s of t minus s of 10. Do we know the position at 10? I think we do know the position at 10. We did it earlier, right? The position at 10 was 80. So I have s of t is equal to the antiderivative v of x dx plus 80. All right, there it is. Pause this video and finish the rest up really quick with another video. So thanks for watching. If you have any questions, please ask me next time I see you in class. And thanks for watching. Bye.